Okay, can I have everyone's attention for a few minutes? So we're crunched for time for a bit at the end of the semester. I just want to get through these last few topics as quickly as I can to give you as much time to work on the projects as possible. So today I just planned a lecture for a half an hour and then give you the rest of the time to work, okay? First of all, is there any questions about Lab 4? Okay, all right, good. So last lecture I was talking about control systems. This was last Thursday. I talked about open loop control systems where you have some kind of top level input. You have a controller. The controller is sending inputs into the plant, which is the thing you're trying to control. And then the plant has some state. So in the case of toasters and dryers, I mentioned that they generally use like an open loop control where you do have the user inputs the color of the toast they want or the dryness of their clothes, but it's really just, the controller is just trying to guess, trying to do the best it can to make the plant do what the user wants it to do. On the other hand, a closed loop feedback controller is where you have some kind of sensors in the plant that feed back to the controller. And what you often see there is the measurement coming back from the plant, which is also called a process variable, is usually subtracted from a set point to produce a signal that's usually called the error, but it really is just how far away are we from the state that we want the plant to be in. And then that error signal is what goes into the controller, and then the controller will send actuation or some kind of signal into the plant, which are called manipulated variables, right? So in this case, in this toaster example, we assume that there's some kind of optical sensor for the toast color, or maybe a temperature sensor. I'm not sure how you would instrument toast, but you would instrument that, you would have that signal come back, and then the toaster would keep toasting until the toast reaches the desired color. In this case, the reason why this is a challenge is that plants often are subject to disturbances, which are invisible inputs that come into the plant that make control difficult. And in the case of the toast, it's that bagels and sourdough bread take a lot longer to toast than white bread. And so the controller presumably would have to compensate for that if you had a good toaster, but no one's invented a toaster that can do that yet. Okay, so so then we talked about how to model both the control system and the plant, and the basic way to do that is through a linear time invariant system. This is basically just an ordinary differential equation. An ordinary differential equation is an equation that has one independent variable, time. And so basically you're dealing with signals that are changing with time. And when you have an ODE, you can have derivatives of those signals and integrals of those signals. But in a linear time invariant system, you can only multiply those signals, derivatives of signals, and integrals of signals by constants, constant numbers, right? So you can't, for example, multiply a signal by itself or square a signal or divide by a signal. So that's what makes them linear, right? So now in reality, the real world is non-linear. I mentioned, examples of that. You have a resistor. People think of resistors as linear, but the resistance actually is a function of temperature. Springs, people think of linear, but springs have non-linearities because they have limits on how much you can stretch them out or compress them. But this is kind of a way to simplify the representation of these systems is through linear. Okay, so with these LTI systems, they're typically transformed into the Laplace domain, or S domain. S is a complex variable, and it's basically frequency. So instead of being functions of time, they're a function of frequency. This makes them much easier to work with. Hopefully you guys remember this from electrical engineering. So whenever you have a derivative of a signal, you just multiply that by s. If it's a second derivative, it's s squared, and so on. If it's an integral, it's 1 over s, or s to the negative first power. Second integral is negative s to the negative second power, and so forth. And you're just multiplying that by the name of the signal. Now things get a little weird with this, with the notation here, because notice here I have dx squared over d squared t. This is the second derivative, right? So this is one way of showing that. This would just be, of course, made s squared. And then x is lowercase here, and notice it's capitalized here. That's another conventional thing. So usually in the time domain, it's lowercase. In the frequency domain, you use uppercase. You also notice that technically, notice I have x of t here. But down here, it's just x. What does that mean? Well, technically, it's x of s, right? But I've used shorthand. There's a lot of shorthand notation with this stuff. And frankly, it gets a little confusing sometimes. So I should have put x of s here. X of s times s squared would be the second derivative of x of t, right? You guys with me? Does that make sense? So it's, yeah. So then we talked about transfer functions. So a transfer function is when you take an LTI and you ascribe to it some concept of an input and an output, right? Which normally, like the equation by itself doesn't have inputs and outputs. It just has these signals or variables, functions of time, right? Or functions of frequency in the case of Laplace, right? So in a transfer function, you basically just have, you represent this as a ratio, output variable divided by input variable. Usually you put that on one side of the equation. And then the other side of the equation is just a bunch of polynomials, or a ratio of two polynomials of s. You guys with me? Now you might say, well, wait a second, man, like what if there's more than two inputs, more than one input, more than one output, right? What if you have a MIMO system, multiple input, multiple output? How's that work? Well, then it gets a little bit more complicated. Then you end up having to do a matrix style representation of this, right? But in the case of single input, single output, you can represent these transfer functions, just as, output over input, right? So really what this comes down to, and just to be clear, what we're talking about is algebra, essentially. You're just taking equations and you're restructuring them using algebra to put them into this form, right? That's what we're talking about, okay? So for example, this example says that the force is equal to mass times acceleration, where x is the position, so the second derivative of x is the acceleration, right? So going to s domain basically means that this derivative just becomes, multiplying this by s squared, x times s squared, right? So that's equivalent to the second derivative. And then f of t just becomes f of s. You don't really do anything to it because it's not a derivative or integral. You just you just go from of t to of s. That's all you do, right? And then the next step here is, if we're going to make a transfer function, we have to assign, like, what's the input and what's the output. Is it the input x and the output is force, or is the input force and the output is x? Well, it could be either one. You could conceptualize it however you want. It depends on the system that you're trying to model. In this case, I said the input is x, so like I'm putting x in and f is, the force is the output, right? The position is the input, the force is the output. So I constructed this as f over x equals, and then basically what I did here was I divided both sides, I divided both sides of the equation by x so I could move the x over with the f, right? Why? Because I wanted to get all of the variables on one side of the equation, right? Or the signals, f and x. And then I wanted to leave on the other side of the equation just stuff with s in it, right? And so that's the transfer function then. So the transfer function is f over x equals ms squared, right? Okay, so that's how you build a transfer function from an LTI. And then here's a little bit more, it's another example, a little bit better example. So this one has u of t and y of t in it. Again, there's two signals involved because it's CSCE, single input, single output. So this one has u of t equals y of t plus the first derivative of y of t. And these derivatives are with respect to t because these are ordinary differential equations. There's only one variable that we're differentiating against or integrating against. So dt, right? And then this is the integral of y dt, right? So all you got to do to get this into the Laplace domain is this integral is you stick an s in here, and this derivative is an s, corresponds to s, multiplying by s, and this integral, it corresponds to multiplying by 1 over s, right? S to the negative first power. So now you've got it in the Laplace domain. Now, as I mentioned, there's no going back. You can't go back to time domain. You're done. Once you go to Laplace, you're locked. You're locked into that. So we got in the Laplace domain, and then at this point, we need to get what's our input, what's our output. I guess y is our output and u is our input. So we're going to say y over u, right? So we need to get y over u on one side of the equation. And then it's basically a bunch of algebra factoring stuff out and dividing both sides of the equation by something and so forth. So you end up getting y over u. Notice in this case I have of s. I didn't have that on the last slide. I mentioned that sometimes you leave out the of s. So you might just say y over u in caps. Okay? But in this case I have the of s. So y of s over u of s is 1 over 1 plus s minus 6s to the minus first power. And there you go. Now, oftentimes, the canonical form is to have the denominator not have any s's to like negative powers in it to make this look like a regular polynomial, which of course you can do just by multiplying this thing by s over s, right? So then the numerator becomes s and the denominator becomes s plus s squared minus 6, right? So you can play those, you could just apply normal algebra rules, okay? And so that's the goal, is to get it into this transfer function form. Now, why are we doing that? What is the point of a transfer function? Why is that important? Well, there's a couple reasons for it. The first is that this is actually the second reason. I would say the first reason is if you have a transfer function, you can find the poles and the zeros of it. The poles are where the values of s that make the denominator 0, that give you basically a divide by 0 error, right? And the zeros are values of s that make the transfer function 0. In this class, we don't care much about the zeros. I mean, there's reasons why you want to know where the zeros are. In this class, we only care about the poles, because the poles are going to tell you whether the transfer function is stable, whether it's bounded input, bounded output stability, right? And I mentioned in last class, if the poles have any, if there's any poles with a real component that's negative, I'm sorry, I shouldn't say that. If the poles have any real components, so for each of the poles, if any of them have a real component, because remember s is a complex number, if the real component is 0 or positive, then it's unstable. It's an unstable transfer function. That makes sense? So another way of saying that is if you want to make sure that all the poles are on the left-hand side. I have a picture of that somewhere here. Yeah. So if you have a plot, so generally, if you have a plot where the real is the x-axis, right? And the imaginary number is the y-axis, you want all of the poles, which are usually marked as x's on here, to be on the left-hand side. If they're all on the left-hand side, meaning the real part of each pole is negative, then you're good. It's stable. Make sense? If that's not the case, then you may still have a stable transfer function as long as you don't give it a bad frequency input. If you give it a bad frequency input, it may resonate and blow up, right? But some frequencies may be fine, right? It just depends on what frequency. So generally, if you want to send all the frequencies in, you can do that. You can do that through what's called the impulse response. So if you give it an impulse, or if you get a step function, which is a square wave, square waves and impulses contain all the frequencies. How's that possible? Well, because so if you have a step function, it's like got hard edges on it, right? You guys know what I mean? Like this, right? If you have a step function, that doesn't look like a sinusoid. But it actually is a sinusoid. What? No, it's not. It's got hard edges on it. Well, you can make this with sinusoids, but it takes an infinite number of them to make this. You have to add together an infinite number of sinusoids to make this. Okay? So thus, if you give it one of these kind of signals, then it's like subjecting it to all the frequencies. So if it blows, typically if you have an unstable transfer function and you give it this, it blows up, right? But on the other hand, you could have an unstable transfer function and give it a certain sinusoid frequency and it might be okay, right? So the step response and the impulse response are a way to test if it's stable or unstable. Now you might say, well, why in the world would we do that if you can just look at the denominator of the transfer function and find the roots of it, right? Well, yeah, but that would only work if you had the transfer function. Sometimes you don't have the transfer function, you got a black box and you just hit it with the step. Like if you don't know the transfer function and you want to know if it's stable, you hit it with the step function or an impulse. If you have the transfer function, then yeah, it's probably best to just find where the denominator, what values of S will give you a zero denominator, right? The poles. Make sense? Okay, so, right, so now this, these pictures came from a simulation, MATLAB simulation. You might say, like, do you have to run MATLAB to get these pictures? As far as I know, yeah, it's the only way. Because you need some way to simulate these transfer functions, right? Now, we're not going to do that in this class. In this class, I just want you to be able to look at just understand that there's, stable and unstable, and we'll just use the transfer function to determine if it's stable. This is just for illustration. You guys with me? So if you had MATLAB, you could actually create this in Simulink and actually see what actually happens when you hit it with a step, right? Now, you might say, wait a minute, I don't understand. If it's a transfer function, functions have independent variables and they have dependent variables. So would not the independent variable just be the input and the dependent variable be the output? And if you want to find this, you just plug the input into the transfer function. No, that's not how it works. The transfer function doesn't really have an input, right? It's just this ratio of two S's, right? You can't just plug an input into it. The way you do it is, in this case, you have to basically take the transfer function of the input, which in this case for impulse is a 1, right? And for a step response, it's 1 over S. So what I'm trying to say, and this is the part that blew my mind, right? The input to the transfer function is actually like another transfer function. It's not an actual number that you just plug into it. Does that make sense? It's crazy, right? I think that's strange, right? So if you want to find like the step response, you have to create a transfer function for the step itself, which is 1 over S, right? And then you multiply that by the function that you want to see the step response of to create a unified transfer function, and that's your new transfer function. Does that make sense? Right? It just blows me away that there's no actual like signal input into this other than, it's like another transfer function, right? That's the crazy thing about this. Okay, so, but how does this relate to controllers? Well, with controllers, right, I just realized that my screen recording was screwed up. Oh well. Sorry, let me go back here. Right, so for controllers, if what you're doing with a controller is you're taking the plant and modeling that as a transfer function, right? And then you take, now that might be unstable, it usually is, right? The plants are usually unstable. But then you take your controller and you model that as a transfer function, right? And then you mash them together by multiplying them. And when I say multiply, I mean literally just multiply them. Literally just take the two expressions and multiply them. That's sometimes called a convolution when it's done in the S domain, but really it's just you're multiplying. So you're multiplying these two to get a mashed together transfer function. And so the idea is that you have an unstable plant, you have a controller, you mash, which also may be unstable. Unstable plant, unstable controller, mash them together, and all of a sudden, surprise, the whole thing is now stable, right? And that's the goal for a the control system design. Now in this case, this is an open loop controller though. This doesn't have the feedback connection, notice. So in this case, what I've done is created an open loop control by just multiplying these two transfer functions together, right? So once you do that, then you can find the transfer function or the stability, the poles of the unified open loop control. Okay, so last time I talked about eigenfunctions. I'll skip over that this time. Right. Okay, so let's look at some other cool examples. So you might have, you guys probably have seen this one in circuit design. So this is a circuit, and circuits are very naturally lend themselves to this type of analysis. So in this case, we have a RC circuit, and there's a switch in here. The idea with this switch is the switch is meant to basically short one side of the resistor either to VDD or to ground. And so basically, if you start out with the resistor connected to ground, right, that's like 0, and then you flip it up to VDD, that's basically creating what is essentially a step response, right, a step function, right? We're going to step that input up, right? And then we can find the way that works, the response of that. So the interesting thing here, though, and you guys probably remember this from circuits, but basically, if you assume that the switch is connected to A, right, in this case, the circuit, you have just this one loop, right? And then you can use Kirchhoff's voltage law to basically come up with the loop equation, right? So that would be VI minus the VO, which is here, is going to be the VI minus whatever the drop is over this resistor, right? The voltage drop. And what's the voltage drop? We use Ohm's law. It's going to be the resistance times the current, right? Does it make sense? Okay, now, what's the problem with this? Well, the problem is we got 3 variables. Remember, I mentioned that these transfer functions are kind of set up to have one input and one output, meaning that you can only have 2 variables, 2 signals. In this case, though, we got 3 signals. There's voltage out, voltage in, and current, right? So that's a problem, right? All 3 of which are time, varying signals, right? So what do? Well, you just basically figure out how to get it to 2 variables, essentially, right? So the way you do that is you take the current equation, in this case, for the capacitor. So the capacitor, you know the current flowing through the capacitor because it's governed by your capacitor equation, which is I equals C times the derivative of voltage, right? So if you take this and you plug it in for I here, right? What ends up happening is you basically kill the I variable. It goes away because you can calculate the current as a function of voltage. And so when you make this simple substitution, you end up having nothing in the equation but VO and VI, which is what you want. And once you got that, you're golden. Then you can create the transfer function very easily, right? Because you're down to 2 variables, right? And not only that, but remember, in this case, we're assuming that VO is our output, because we want to know what the response is of the VO as a function of VI, right? And remember, VI is going to be a step, which is 1 over S, when we actually plug everything together. So so basically you get into this form, and then once you do that, the Laplace transform is trivial because all you've got is really one derivative here. So you just got a 1s, right? You just get 1s in here. Everything else kind of stays the same. It just goes from a function of I to function of s, right? And then use some algebra, and you can come up with a transfer function, which in this case is VO over VI equals 1 over 1 plus RCS, right? And R and C, of course, are constants because the capacitance and the resistance, right? And then if you want to find the step response, like what happens if you turn on that switch. Actually, let me back up here. So I talked on Thursday about the eigenfunctions, where you can actually take this and convert it to time domain. And I did that. And the voltage, when you do that, the voltage goes down, right? It goes down. And I'm like, that's not right. That's not right. If you turn that switch on, it should charge the capacitor, right? Voltage should go up. not down. Why is it going down? And I sat there thinking, like, what am I doing wrong? Well, what I forgot was I forgot to put the actual switch transfer function in, right, which is the 1 over s, right? So when you multiply this by 1 over s, right, to create a unified transfer function, you end up with what you would expect, which is this red curve here. You turn on the switch and charges up the capacitor, right? Which you can actually do this one through an eigenfunction transformation. You can actually do an inverse Laplace it takes more algebra. I was going to put it on here, but it's a lot of tons and tons of equation solving. But you can actually do an eigenfunction transformation here and actually get this exact curve. And by the way, I mentioned, I don't know if you guys remember in 611, there's a lecture in 611 at the end of the semester where we talk about RC delay. We talk about Intel's like 5 gigahertz processor, man. And it's like, okay, but like, I know you're real proud of that Intel, but like, why not 20 gigahertz? Why not 100 gigahertz? Why are we stuck here at 5? Why 5? What's going on? Like, what's the challenge, right? Well, the challenge is the RC constant, right? So CPU is just a bunch of resistors and capacitors fundamentally, right? Every transistor is a capacitor. Every wire is a capacitor as well as a resistor, right? So you got this, basically the delay it takes to charge that guy up is R times C, right? And I always wondered about that. I was like, wait, well, hold on. Let's talk about units here for a second, right? R is ohms, C is farads, time is seconds. You're telling me that if you multiply ohms times farads, the resulting unit from that is seconds? How, right? Well, I still don't know the answer to that. But the RC constant, it can be derived literally from this transfer function. So if I do my eigenfunction transformation, you can actually see that the time it takes to charge up is just coincidentally R times C. It takes R times C seconds to charge that bad boy up, right? And so this is the first time where you can actually derive it, right? Still don't understand the units thing, though. Doesn't make sense that ohms times farads is seconds. That's bizarre, but okay. All right, so then you can do stuff like, I'm just going to go through this real quick. Maybe I shouldn't. No, I'm not. I'm going to skip that. Never mind. Okay, so let's take another really quick example here. Let's look at instead of a circuit, let's look at a spring. This one blew my mind too. This blew my mind. I couldn't believe this. So it turns out that a spring is the same as an RC circuit. Why? Well, okay, so X is the position. So imagine you have a weight that's connected by a spring to a ceiling, right? And say the force that you are imparting on the weight is U of T, right? So that's like the input into that's me being a jerk and pulling that down, right? That's me. That's a human imparting this force, right? There's a couple ways to look at that. That's just the force acting on the object hanging by the spring, right? Then you have X, which is the position, right? So this gets weird because these variables represent different quantities, right? This is newtons and this is meters, right? But they're named U and X, right? Okay, so, you could define I should say ODE, but basically the force is mass, the mass of the object, of this, whatever this is, weight, this mass, mass of the weight, mass times acceleration. So the acceleration is the second derivative of x, right? Now notice I'm switching the notation here again, and there is a reason for this. Don't I have it? I thought I had it somewhere. I thought I had it here somewhere. There's different names for these notations. Okay. Well, anyway, Yeah, one's Newtonian, one's Lagrange, and one's Leibowitz or something. I can't remember the name, but they're all basically ways to represent derivatives, right? So I think this is the Newton one.
It's Newtonian derivative.
So Newton was like, Newton didn't believe in the whole dx over dt. He's like, that's dumb.
More space, more Latin.
He's like, just put 2 dots over the variable, right? Right? And we're done with this, right? Yeah, so x dot dot is the second derivative, right? When I was in school, when I did this, when I was in calculus, it was x apostrophe apostrophe. We used apostrophes.
Yeah. I forgot what notation that was specific, but I know what you're talking about.
Now, I don't understand, like, why the apostrophe versus the dot versus the dx over dy, like, or dy over dx? Like, why are we doing that? What are we doing here? What are we doing with this? Why? Why are we doing this? Why is there 3 different notations for this? This is insane.
There's several notations of vectors.
Yeah, it's like, you're right, that's true. Vectors have sometimes an arrow. You're right, that's a good point. But this is especially confusing to me. This is just ridiculous. But anyway, we got the x dot dot, so that means second derivative of x. And then we're going to put that on one side of the equation because it turns, you guys probably know this, this is fresher in your mind than it is for me because you guys just had physics, right? But it turns out that you have to equalize, the total force is equivalent to, in this case, 2 things. Whatever force is being imparted here, right? Right? And also the spring has a spring constant, right? So notice that this is positive because I'm pushing this down. I'm putting positive force, right? But notice this is negative. Why? Because the presumption is that the spring is resisting me, right? The spring is trying to pull up. The spring is literally putting a spring force, which is opposite. The spring's being a jerk and trying to resist me as I pull down, right? That's why that's negative, right? And that's equivalent to the total force. So then you can convert this to Laplace. The spring constant is K in this case. That's just how stiff the stiffness. K is stiffness. And then you can create the transfer function for that, right? Does that make sense? So it turns out that is this stable or unstable? No, it's so to find the roots of that, you find the poles. The poles, remember that remember that the we need this to be negative, right? Because K is not negative, right? M is not negative. K is the spring constant. That's not negative. That's positive. The mass is not negative. You can't have negative mass. It's impossible, right? So this is positive. So how do we make the denominator 0? Well, basically s squared has to be negative, right? How do you make s squared negative? Well, imaginary, it's got to be imaginary, right? But if you square something, right? If you square a negative, like a real, like, you know, a negative number you square becomes positive, right? But if you square I, it's negative. So the poles are actually plus and minus the square root of K over M times I. Well, guess what? There's no real component here at all. It's just imaginary. But that's not good enough because in order for this to be stable, the real component has to be negative, right? So technically that's unstable. Right? So someone might say, well, how is that unstable? You're telling me that this thing can go infinite? No. How? Well, if you have a spring and I go like this and I start and I put like this certain frequency into it, if I put the natural frequency in, this thing will go bigger and bigger. Imagine if you had a weight. Say I was holding a thing and I had a spring on it and I went like this. And the spring was going like this, and I was going like this, and you hit a certain frequency and it keeps getting bigger and bigger and bigger. Now you might say, well, yeah, but I mean, eventually the spring's just going to break. That's because it's nonlinear. True, but there's something else happening there too that's making it actually bounded. It turns out that in addition to the spring, there's also a dampening factor. The dampening factor is the spring generating heat. Did you guys know that? If you take a spring and go like this with it, it gets hot. It gets hot, right? You actually transfer some of the energy into the spring, and it turns out that that's the same as a resistor. And it turns out that this is actually a resistor, not a dampening factor. Well, I mean, it can be, like calculated that way. Resistors also get hot when you run current through them. And then the spring is basically a capacitor, right? That's pretty cool, right? So anyway, I basically, to incorporate the dampening factor is a function of the first derivative, right? This is like friction. So with friction will fight you, but it'll fight you more if you go faster. If you go slower, no problemo. But you go faster, the faster you go, the more friction acts against you. That's why this B, which is the dampening factor, is multiplied by x dot, which is velocity, right? Make sense? So anyway, you figure that out and you get a new transfer function. And this one, I believe, is this one stable? I forget. Yeah, actually, it is, right. So this one is, I had to use the quadratic equation for this one. It wasn't just, this one was harder to find the roots of. No. But, yeah. Anyway, you can also calculate the natural frequency too once you have this, which is kind of neat, but that's not super important for us. Okay, so, all right, so, okay, there's just one more thing I want to get through today, and then I'll finish this lecture on Thursday, okay? I just have to get to the discrete control. One thing, one last topic here that's important. So I mentioned that when you convolve, right, you take two transfer functions and you mash them together. That creates the open loop transfer function, right? The problem is no one uses open loops except dummy toaster manufacturers and dryer manufacturers. Most control systems are feedback control, closed loop systems. So how does that work? How do you calculate the transfer function? Well, it turns out it's just algebra. It's still just, it all boils down to simple algebra. At least, because we're keeping everything simple here. So this is a closed loop, right? Controller, plant, difference, subtract, right? Then, how many variables we have here? Well, we got a problem here. We got a problem. There's 3 variables. That's no good. No one knows how to do a transfer function with 3 variables. I don't think anyone knows that. So how do we figure this out? Well, we want to know, what do we want to know? What is our transfer function supposed to be? What's our output and what's our input? Well, I would say our output is this guy, whatever this is. This is the state of the system. It's the output of the plant. It's the state of the plant. It's like how fast your car's going if you're trying to control cruise control, right? I call it YCL, closed loop. This is the kind of the state of the system, right? This is the process variable for the plant, right? But the input is really not E of S, nor is it whatever this is. I didn't even label that. That's the 4th variable, actually. I don't even label this one. I don't care about error. I care about ref, RRef. That's the set point. So what I want to know is, what is the closed loop response with respect to the reference input, right? So how do you figure that out? Well, again, you just use algebra and a bunch of substitution. So the closed loop, right, is this minus that, RF minus YCL, right? You might say, wait, you can just subtract stuff in the S domain? Really? Yeah. Yeah, you could just do that, right? But then you're multiplying it by GP, GC, right? So remember, open loop is this times this, right? And then multiplied by this, right? So yeah, that closed loop is these guys, these 3 terms, this, and this multiplied against one another. And this, I actually took out this and I replaced it with RF minus YCL, right? Okay, then let's see. You distribute these here. You bring this guy over to the left-hand side of the equation. You factor out YCL here. And then you divide both sides of the equation by 1 plus GPGC, so you have this. And then you divide both sides of the equation by RF. You guys with me? So you end up with YCL over RF this is the open loop transfer function, right? Plant times controller, right? Sorry, controller times plant? Do I have that wrong? It's this times this, right? Why is it reversed?
Well, the order doesn't matter.
Order doesn't matter. Yeah, you're right. It doesn't matter because we're still associative here, right? Yeah. So it's multiply, it's associative. The order doesn't matter. GP times GC, so this is the open loop, right? Divided by 1 plus the open loop. So this is the canonical closed loop transfer function equation. If you know the open loop, you just divide it by 1 plus the open loop and you get the closed loop. Make sense? Okay, so yeah, so in the next lecture, I'll end it there. In the next lecture, I'll talk about how we discretize this. Because remember, I mentioned on Tuesday that none of this is possible to deploy in a digital system, right? This is like greenhouse stuff, right? At some point, we need to put this in something that a computer can actually implement. Okay, so I'll talk about that next time. That'll be our, and then we have one more lecture after that for real-time systems, and then we'll have all the material for the semester. Okay? All right, sounds good. Thank you.